Welcome to Breadboarding. This is video 43, part 1 of the Breadboard 8088 PC project. In this video, we're going to be adding the design for the IDE Hard Disk and controller. So in the previous videos, we've been modifying the floppy disk controller to use programmed CPU controlled I/O rather than direct memory access, DMA, because we had a few issues with the DMA controller. And in this video, we're going to be adding a hard disk and controller and configuring a BIOS that knows about the IDE drives. Now, in the Nanocomp 6809 project I did some 12-18 months ago, there'll be a link to the video in the top right hand side here. I did look at adding IDE Hard Disk to that project, so I have already gone through a number of these slides already. But when I was looking at what type of hard disk to add, I did consider early 1980s hard disks. So drives from this sort of era were sort of full height 5¼ inch disks, and generally known as MFM or RLL, and tend to have capacities of about 10 to 110 megabytes. Now these didn't have much electronics actually on the drives themselves, and the controllers were quite complex, and they're fairly rare now and unreliable. In Adrian's Digital Basement, there's a video that shows him diagnosing some problems with one of these drives, and in fact then taking the cover off it when one of them had actually failed. And you can see from the pause video here, with the top off, we've got the disk platters, the drive head, and the head mechanism that moves it across the platters. And in fact, in this particular drive, it was this mechanism that had actually stopped working. IDE stands for Integrated Drive Electronics, and this basically took most of the controller functionality and put it into the drive package as well. So it greatly simplified the interface. And these were introduced from around 1986 onwards in the Compaq Despro 386 range. Now you can still get original IDE drives on eBay, they're about £20–30, but I thought that they're probably a bit too much trouble, especially as drives of that era probably still need 12-volt power supplies as well as 5 volts. So what I'm going to do is to use the same mechanism that I used in the Nanocomp 6809 video. So I do have a spare SATA serial ATA modern drive with which is about 500 gigabytes, which is way too big for the versions of DOS that we're trying to use to make full use of, but we can probably make use of 32 megabytes to 2 gigabytes probably, depending on the version of DOS that we're using. Now I'm using this with a StarTech 40-pin IDE to SATA converter. So this plugs into the SATA socket on the drive, and on the other side here, you can't see it here, but there's a 40-pin IDE connector, and this little microcontroller thing actually does all the conversion necessary to make this modern drive look like older IDE drive. Now this is an extract from the Compaq Despro 386 manuals from around 1988, and this shows on the right here, this is the IDE drive connector, and you can see here that the IDE interface includes D0 to D7, D8 to D15. So it's a 16-bit interface, and on computers with a 16-bit bus, so 286s and 386s for example, the interface provided by the IDE controller is very straightforward. Basically just provided 2 bidirectional buffers for the D0 to D16 address lines, and a few other bits of logic, and another buffer for some of the other signals here. So the original IDE controllers were very simple and straightforward. However, because we've got an 8-bit 8088, then we need to do a little bit more work to actually allow the 8-bit CPU to be able to talk to the 16-bit IDE drive. Now this is the schematic of the design that I based the 8-bit IDE controller used for the Nanocomp 6809 with a standard 16-bit IDE drive. And you can see it's made up of 5 chips, so we've got one PLD that handles some of the control logic, we've got 2 bidirectional buffers, and we've got 2 latches as well. Now this design read and write data to the IDE drive using the same byte order, so most significant byte, then least significant byte. And the reason why this is important is that the design that we'll be looking at uses a different order for reading and writing. This simplifies the design a bit. The reason why we need to have latches on both the upper and the lower bits is because of this requirement here. Now these are some of the references that I've used, so all of these will be included in the description below the video. This first design that I've just shown you here from Lee Davidson's site we've already looked at already. We've also got information on the IDE ATA specification. Now, getting access to the official versions of those, you have to be a member and pay a membership, but this draft version, which is available, I'll include the link there. There's another design that we'll be showing in the next slide or so, and then the XT-IDE project. This is a project that allows more modern disk drives to be used with older XT class machines, and it also includes the BIOS code necessary to make this work. The latest version being the XT-IDE Rev 4 from Glitchworks, who make a kit available if you want to buy one of these. So if we just have a look at some of those links. So this was the design I've already shown you. This links off to the PDF of the ATA interface specification. So if we were writing the software to access this, so for the 6809 project I needed to actually work out what the various controller commands are. Fortunately for this project we can just make use of the XT-IDE BIOS, so all that hard work's done for us already. Then in the Vintage Computer Federation forums, the XT-IDE project page started here. There's then the Rev 2 board, which made some enhancements and added some extra functionality. The XT-IDE BIOS, which we'll be downloading and building probably in the next video, part 2. And then the latest Rev 4 version, which is from Glitchworks. All of this is open source, so the schematics and things are all available. And this actually includes some information on the timing that I'll show you and talk about in a few minutes when we look at the schematics. I'm not sure we'll need to worry about this for the drives that we'll be looking at, but this provides some background. So this is a design that once I'd done the 6809 project, I came across this design, and it includes actually a simpler design which just has one PLD for I/O decoding and another for the control logic, and then these two chips which are 74LS 646s. Now these are chips I've not come across previously. They're quite difficult to get hold of. I managed to get some on eBay, but you can't buy them new from any of the main distributors like Mouser, RS Components. Now these chips actually are known as octal bus transceiver and registers, and they actually behave almost like a bidirectional buffer plus 2 latch chips, in that they actually have latches which are able to latch the data going from A to B and also from B to A directions. So they have 2 lots of latches, unlike the 573s which only have latches on one side. Can ignore the real-time clock in red down the bottom there. Now this is the XT-IDE Rev 1 schematic. The schematic's a little bit tricky to get your mind around because a lot of the bus signals are not actually joined up, so you have to kind of do that in your head. So what I have done here is just, we've got over here the ISA connector, so this is the standard sort of slot connector for the PCXT. And we've got here the 8-bit data bus going through this buffer here. And then this buffer not only connects to the D0, D7 lines on the IDE connector here, but also then is used to feed the other 2 latch chips. These 2 latch chips being fed from the data bus on either side here are then connected to the D8 to D15, the upper byte of the IDE controller, and one is used for reading, the other is used for writing. And then some of the clock signals and the output enable signals are then decoded down here. Now this area here needs a little bit of work to actually work out how to decode it, and on the Rev 4 board, which is the latest board, there's some enhancements where the default mode compatible version 1 has the J1 and J2 jumpers set in one position, and then the high speed modification has it in a different position. And what this fundamentally does is reverses the A0 and A3 address lines to control the way how the upper and lower byte are addressed when reading and writing data to the controller. If we zoom in here, we can see that the A1, A2 and A0 address lines are decoded here together with the IDE chip select. So these outputs here are only enabled when this combination here works, and then the decoder here takes the IO read and IO write, which are both active low, and the A3 line to provide the signals necessary to drive the clock inputs on the latches and the output enables. And what I have done is decoded this in a spreadsheet and worked out how these rules work. You also see over here this logic over here controls the CS1FX and CS3FX. Now in fact these are also known as CS0 and CS1 rather confusingly. So this one can be CS0 and this one can be CS1. Now in fact this 1FX and 3FX refer to the I/O ports on the original Compaq Desk Pro. So these were the designations actually given it on the Desk Pro, and it seems to have then actually prevailed into the ATA standard, although in later versions you'll see it as CS0 and CS1. This is the reason for this confusing label. There is a bit of logic down the bottom here related to introducing something like a 20 nanosecond delay into some of the read and enable signals. Now the Rev 4 web page that I showed you includes some background to this timing. I suspect we probably don't need to worry about this because the speed of which this is operating at is not likely to cause problems to this, but it's something we might need to bear in mind that for certain high performance IDE drives then this was an issue. I'm not sure with the converter that we've got that this is going to be an issue, but something we'll ignore for the moment, keep it simple, but we might need to come back at this at some later point in time. So the IDE Disk Controller Interface is mainly contained within the disk drive itself, and the IDE ATA interface uses 10 registers. The main inputs really are the A0, A1 and A2 into the disk drive, and the CS0, CS1 or our CS1FX, CS3FX, which is the alias for those. And so that's how we control which of the 10 registers we access. Now in fact when we've actually got the CS3FX selected, then there's actually only 2 registers in the standard disk drives, but in fact the XT-IDE design makes use of the lower 000 value when we've got that bit set for the high byte in the data port. Now when in fact the high performance mode is enabled in the Rev 4 board, then in fact it remaps the A0 and A3, and so this means that these 2 ports are actually together, and a single word command can be used for reading and writing data to the port rather than 2 separate byte commands. Now I should also say that the CS0 and CS1 are not used to select between drives, and the majority of the registers use CS0. There's only these 2 at the end that use the CS1. The drive selection is actually done by bit 4 of the LBA3 drive head register. So this particular register here, there's a bit there that controls whether we're dealing with the primary drive or the secondary drive, or master and slave in old terminology. And the way how the XT-IDE BIOS actually interacts with these ports is it uses the BL register as a bit mask to switch between the upper byte and the lower byte, and this bit mask being 08, so that means the A3 address line is masked out there. And we'll see in the code in a page or two's time that it uses an XOR logical function to toggle the A3 line between the 300 low byte and the 308 high byte. Should also note that CS0 is active on writing the low byte, but when writing the high byte, the CS0 is actually inactive or high, and so the disk controller will actually ignore any of the signals going to the disk controller when we're actually writing the high byte. It's only when we're actually doing things with the low byte that the actual disk drive itself will take any notice of data on the data port. So this is an extract of the XT-IDE BIOS code that actually does the reading and writing to the IDE ports when it's in the version 1 compatibility mode. And before this code's called, then the DX register is set to the IO port base address, which is 300, and the bit mask is set to 08. And we can see here that what it first does on reading is reads the lower bytes from 300 into AL, then it toggles the bit on the DX register to change it to 308, writes the byte in AL to the memory, and then inputs the upper byte from 308 into AL, toggles the bit back again to point back at 300, stores the byte, and then this code is repeated a number of times. And I think in the code this macro in fact is included 8 times, so it will read 16 bytes in one section of inline code. And then for the writing, then rather than reading the lower byte then reading the upper byte, this writes the upper byte, most significant byte first, and then the least significant byte. And what this in fact does is does a word read of the data from memory to write to the disk into AX, and then it switches from pointing to the lower byte to the upper byte first of all, switches the data around in AX so that we then write the higher byte out to the controller first. We then switch from 308 back to 300, the lower byte. We switch our byte values around again so that AL now has the lower byte, and then we send the lower byte to the IDE controller. That's actually incorrect, that should be lower byte there. We send the lower byte to the IDE controller. Now, because we do the order of these slightly differently, then it does mean that the design can be a little bit simpler. We just need a buffer for the lower byte, but we need latches for the upper byte. So this is a diagram I put together to explain how these various signals interact for the read. It's quite complicated, but distilling these values, by doing this, it helped me to understand it and able to actually put the rules into the PLD design more easily. So we've got here the IDE connector with the D0 to D15 16-bit addresses. We've got our CPU 8-bit address bus. We've got our I/O decoder. So this was the I/O decoder we added for the real-time clock a couple of videos ago. And this takes the address bus and the read and write, I/O read and write control signals and decodes them. We've got the upper byte and the lower byte. The directions we're talking about with these chips is A is on the CPU side, B is on the disk drive side, and when direction is 1 or high, then we're going from A to B. When we have a low value on direction, then we're going from B to A. So our I/O decoder has been extended to take these signals and to actually provide an additional IDE chip select, and this is for the default XT-IDE BIOS 300 to 30F address range. One thing we do need to note is this tends to be the default address I/O port for certain adapter cards, particularly perhaps network cards and possibly sound cards and things like that. So we just need to be aware of that in the future. And then the I/O read and I/O write and additional A0 to A3 lines are then also used to produce the necessary control signals to control the latches and to send out to the IDE drive. So for reading, we're going to read the lower byte first and then the upper. So when we read the lower byte from 300, I/O read will be 0 and direction will be 0. So with direction 0, it means the data will be coming from the IDE controller along here and out to the CPU bus to the CPU. And you'll see here that we also do the output enable on this, so it means that the data coming from here can flow out through here onto the data bus. So the least significant byte or lower byte comes out on the data bus and is read by the CPU. At the same time, what also happens is that the direction is the same here, in that it will also be direction 0, so it's data coming from here to here. But what we're doing here is we're doing the clock CBA, and what this does is clocks the data coming on the B port and actually puts it in the A register or A latch, but it doesn't enable the outputs here. So the data is actually saved from the upper byte here and saved in the latch here, and then when we come to read the upper byte at 308, you'll also see then that the 308 chip select will then be enabled as well. Now this doesn't actually do anything with the registers in the IDE drive itself. It ignores the access to here because there's nothing actually on port 0 in this particular case. But what this does do is then enables the upper byte output enable on this latch, and because we also have the select BA is set to high, so this means we're reading the latched value, not the live value coming through the port here, and so we then are able to read the upper byte. So this is quite complicated to work through, but in fact the rules for doing this are fairly straightforward when implemented in the PLD. And then for doing the writing, it's a little different in that we've got the same information that we've got here, the I/O port decoding, but the write order, we're doing the upper byte first and then the lower byte. So what happens here, when we write to 308, I/O write is now 0 and direction is 1. So this means that the direction we're going here, when it's set to 1 or high, we're going from A to B. We can see here that CS3FX, or the CS1, is set here. So the disk drive itself here will ignore whatever's going on the data because it doesn't actually decode that. But at this point in time, the data here will be going from the address bus into the latch here. The clock AB will actually latch the upper data here into this latch here. So the data will be here, but at the moment it's not made visible to the IDE drive. So then when we come to write the lower byte to 300, and we'll see here that now we have the other CS line, so CS1FX or CS0, that will now be enabled. And the buffer here, direction is 1, so it's going A to B, and we also do the output enable. So this means the data can flow from here through the buffer and out to the IDE drive. And at the same time, what we're also now doing is we're actually enabling the output here. And because again the direction is going from A to B, what this is now actually doing is sending the data from B register out to the IDE drive here. And because the SAB is set to high, that means we're taking the latched data, not the live data coming through the port here. So by using this chip here, by providing the 2 clock signals that we use here, then this enables us to remove the need for having 2 chips. So our breadboard PC IDE disk controller is going to be based on the XT-IDE Rev 4, but we're going to replace the 2 latch chips, the 74LS573 chips, with a single 646 chip. We're also going to use a programmable logic device that will minimise the amount of bus wiring and chips we need. We're going to use the Rev 1 compatibility for the moment, so it'll just be a little bit simpler to understand. We're going to configure the XT-IDE BIOS for tiny modes. This generates a 4 kilobyte executable, and with Rev 1 compatibility with the I/O port with a default of 300, and that will now allow us to fit the first 4K of the 32K BIOS EPROM to be the XT-IDE BIOS, and we're going to shuffle the main BIOS, the XI8088 BIOS, rather than starting at F8000, it will now start at F9000, and that means that there is enough space in there for it to shuffle up. And then we're going to be using our 2.5-inch portable SATA drive with the IDE interface adapter. Now, one of the things I did come across here, if you're using an existing drive that's being used with any of the later versions of Windows, then modern Windows versions use GPT, boot sector and partition tables. Now these are difficult to remove with MS-DOS, certainly with early versions of MS-DOS. Versions of F-Disk from perhaps Windows 95 onwards do have the /mbr switch, which might allow you to overwrite it. But if you're trying to do this with MS-DOS 3.3, for example, then it's difficult to do. So you can either wipe the disk with disk erasing software such as DBAN, which does take quite a long time, I think sort of 6 or 7 hours. But I did then later find out that Windows 11 DiskPart is able to do this in minutes. However, you do need to be careful to select the correct disk. If you were to select disk 0 is like to be your boot disk, so you could actually damage your Windows installation if you're not careful. You're certainly going to need to select disk 1 or even a higher disk number if you've got multiple disks, and then the clean all command will actually zero out all the partitions and also will erase the boot sector as well. And this should mean that early versions of MS-DOS will then actually be able to partition and put the boot sector on this without any compatibility issues. Now pretty much come to the end of this explanation about the design. We'll just have a quick look at the schematic and then I'll break the video, and in the next part of the video what we'll look at doing is starting to look at programming the PLDs, laying out the board and building the XT-IDE BIOS and seeing whether or not we can try to boot MS-DOS off the hard disk. So here's the schematic. It's getting quite busy. There is a new version of KiCad 804, I think, which is a bit more stable than some of the earlier versions of 8.0. Down the bottom here we can see that this is the real-time clock and the I/O decoder we added in some of the more recent videos, and in fact what I've done here is, because we had a few spare lines on here, we've now got the chip select for the IDE controller is now here, and the I/O read and I/O write signals now being buffered for this and go down to the IDE disconnector, And then we can see here that we've got our programmable logic device, which is providing a lot of the control signals for the 74LS646. So this is our octal buffer stroke latch, which has got latches in both ways. So we're connecting that to the upper D8 to D15, and then the buffer is just connected to our D0 to D7. So we're going to be looking at this in a bit more detail when we lay the board out and when we wire it all up, but I'll leave that for the next video. So if you don't want to miss out on future videos, please hit subscribe, and if you can hit like, it just helps to make the videos available to more people. Thanks for watching.